So the outline is that we have part A, is the glass is half full, and part B is the glass is half empty. Now, for part A, the point is to make deep nets accessible to the masses. And for part B, we want to advocate a combo of part A with stuff that's decades old in AI and centuries old in linguistics. And then I do want to call out the link at the bottom of every page, which has pointers to code and examples and more. So here's this general fine-tuning little language. It has 4 or 5 functions, 4 main arguments, and we'll show lots of examples of this. The standard recipe for deep nets looks like this. There are 3 steps. You start with a pre-trained model, and then you add to this fit and predict. And we're going to emphasize fit and predict. The terminology is borrowed from sklearn. You start with a pre-trained model, you add to it some data, and you get a post-trained model. And for predict, I take an input X, I apply a model, either pre-trained or post-trained to it, and I get a prediction Y hat. And hopefully the predictions Y hat are close to the gold standards Y. This is pretty much all you need. These programs are short, typically 1 line, and there's not a lot of programming, certainly no Python. And the examples and the standard hubs, I think, are unnecessarily long and complicated. It shouldn't be any harder than this. So here's an example of a fit program in which it starts with a pre-trained model, and then you add some data, and you get a post-trained model as output. And then at prediction time, you enter an input X, say, I love you, and then you get an output label Y hat, say positive, and you get a score associated with that, which is how much we believe that Y hat is the right answer. Now I want to talk about portability. If you can put H there, or you can put P there, and in one case you get 1 hub, and in another case you get another hub. And why do you need portability across multiple hubs? Well, you'd like to hedge across supply chains given current world realities. But actually, Unix really did very well surviving the test of time because it wasn't tied to any particular company. So here's an example of a data set. We're going to have these equations. Equation consists of a task and some reference to some columns in the data set. Here's some more equations for glue tasks. Some of you may be familiar with the standard glue benchmark, and it has 8 or 9 subtasks. And here's one equation for each subtask. It makes it pretty much a 1-line program for each one of these. Most of these tasks are classification, but one of them is regression. And then here's some more tasks that go beyond glue. Here's some examples of tasks. In classification, the Y, the gold standard labels, are in a small set of classes. We can think of them as integers or strings. Those are categorical variables. For regression, the output is either a point or a vector. And then for question answering, say squad, the answers are basically spans of substrings of a document, and you say where the beginning or the end of every substring could be. And for classified tokens, you have a classification variable, not just one per row, but you have one for every token. And speech recognition's got something else. These are all different ways of setting this up, but they all pretty much look like classification and regression. And there are these, Hugging Face has some nice user interfaces so you can search around and look at models and data sets and so on. Here I'm going to refer to a model as F, could be either pre-trained or post-trained. And so here's some examples of pre-trained models, and here's some examples of post-trained models, and then here's some examples of a translation task. Here's another task of token classification. You've got many of these models are post-trained for one task or another task. Here are 7 simple examples. So the first one is summary. So you can take either a model, a data set, or some other things, and it'll describe whatever that thing is. The second example that you can use this as a search engine. Go find me some data sets or models that have emotion as in their names and sort them by popularity. Predict is, well, we saw some examples of that. The default model does sentiment analysis, but if you specify a model, say an emotion model, then you get emotion classes. This is the named entity recognition. Fill mask is another task. Most examples we saw predict, they read from standard input, but you can also read from a data set. So as we said, the glass is half full. This is pretty much all you need to cover much of the recent excitement in the literature. It's amazing how much can be done with so little, no real programming. This demystifies deep nets. Nobody would suggest that regression-like methods are artificial intelligence. And that's the three of us here. Now, the other three are going to look at using traditional views in AI. So let me talk a little bit about this history. A lot of people point to this quote by Firth, "You shall know a word by the company it keeps." Patrick Hanks and I wrote a paper 30 years ago on what's now known as pointwise mutual information, and we quoted Firth and some others. Word2Vec came along a little later, and now BERT, but pretty much all of these follow the same tradition. They're all basically collocation-like methods. And by construction, these methods look for words that appear near one another more than chance. The strength of these methods is they're really good on fluency, and they're pretty good at things that psycholinguists refer to as word association norms. They also have plenty of weaknesses, and we're going to talk about some of these opportunities for improvement now. Semantics. If you ask a robin is a blank and try to fill in the blank, Bert will say fill in the blank with bird. That's good. But if you say a robin is not a, it also comes up with bird. And there aren't very many things that could be wrong, but bird is one of them, and it comes up with that. Now, what's going on? Well, with collocations, there's really a difference between collocations and synonyms and antonyms. By construction, these things look for words that appear near one another a lot, and both synonyms and antonyms appear near one another because corpora are full of comparisons and contrasts. Compare and contrast this and that. Moral is closer to immoral than either is to good. And so there's a difference between collocation and synonymy. Hallucinations in possible worlds. These models have a tendency to make stuff up. Often the stuff they make up sounds plausible, but the embellishments just aren't there. Language models have a tendency to come up with alternative facts faster than we can fact check them. And this might be their most dangerous weakness. People might actually believe some of these conspiracy theories. So here's an example. You start with the bold stuff as a prompt, and then GPT-3 generates all the rest of this. In the beginning, it seems kind of reasonable for a while, but it doesn't take long before it gets more and more suspicious. This stuff tends to wander around aimlessly in infinite loops, and there's been a lot of stuff written in the literature about methods to do better than that, and Grice is just one of many of these things. We have some experiments we'll talk about with time and space, and GPT-3 is maybe at chance or a little better than chance on these things, but it clearly doesn't understand even very simple questions such as these. Here are some other problems that are maybe a little timely. There's a huge amount of literature on time and space and many other topics. We'll only touch the surface here. But in general, what's going on is that we believe there's a kind of rich set of connections between syntax and semantics. But what we're trying to argue for here is that one could do various short-term fixes to address some of the concerns we mentioned, but it's probably better in the long term to try to come up with something that takes seriously an interdisciplinary approach, combining some of the recent advances in Part A with stuff that's decades old in artificial intelligence and centuries old in linguistics and philosophy.